So, good morning, and we start with our second lecture on simple linear regression. So yesterday we set a stage and we started from very basics, from the line equation. Then we saw the various parameters in the line equation. We had the alpha, the beta, we needed to estimate those values, and finally we reached to the confidence intervals. There we found then how best the goodness of our line is. We defined a term, we call it r squared, and by that we could know how best we fit our model. Okay, now today we start by talking about linear estimators. Okay, now what are linear estimators? With the help of these we estimate our alpha and beta, the intercept and the slope. Okay, so it can be written in this form. Okay, summation of wi yi. Okay, where wi is finite constants. Okay, so in simple regressions we have alpha hat, the estimator of the intercept, and beta hat, the estimate of the slope, and which takes a linear form. Right? Now, unbiasedness. Okay, we need our estimator to be unbiased. Okay, so for this we have these properties. The expectation of the intercept, of the predicted value of the intercept, must be equal to the true value of the intercept. And similarly for the slope, the expectation of the predicted slope must be equal to the true value of the slope. Okay, how this is possible? Let's have a quick look into the derivation, or to prove the expectation of the predicted value of slope is equal to the true value of the slope. Okay, so for this we will just use the assumption that expectation of the random errors, the disturbance term, which we cannot get from our data, which is caused by some external variables, the expectation of those is equal to 0. Okay, so now to prove that this expectation of the predicted value of beta is equal to the true value of beta, so for this, now just put here in place of wi the values we knew before. So beta hat we derived yesterday, it was in this shape, right? Now take this value as a constant, call it Ci, okay, and we have yi. Yi is our model. Okay, let's replace it here. In place of yi we put equation of our model. Okay, it takes this shape. Now multiply each term here, okay, with alpha, then with beta xi, then with the disturbance term. Okay, we multiply all of these, we have this equation. Now factor the constant out, alpha from here, beta from here. Okay, it takes this shape. Now divide each term by this. Okay, so we have this form now. Clear? Okay, now by identity we know from yesterday that this summation is equal to 0. Okay, and then we have another identity which says that the difference between the observed value and the mean multiplied by the observed value is equal to the square of the difference between them. Okay, this is another identity which we can prove just by adding. If we add here xi minus x bar, we can prove this identity is equal to this. If you want to know, I have the proof here, we can discuss after the lecture. Okay, so we will use these two identities here. Okay, so in place of this we will use this identity, okay, we'll replace it, and for the others we have 0 here, okay. So this term is 0, summation of this is 0, so 0 multiply alpha. Then for this term we say by identity this minus this is equal to x minus x bar squared, okay, by this identity, okay. So these two terms cancel out, we have just beta and the rest of the term, okay. So now beta hat is equal to beta plus summation of this term, okay, which we can write in compact form as beta plus call all of this term as ci, okay, and we have the disturbance term, okay. Now what was our goal? Our goal was to prove expectation of the predicted value of the slope is equal to the true value of the slope, okay. Now our equation is in this form. Take expectation to both hand side, we have expectation of beta, expectation of this term, okay, but here in this term these values are constant, okay. So ci we can take it out of the expectation, we remains with expectation of the disturbance term, okay, and we know from yesterday the expectation of the disturbance term is equal to 0, okay. So if this is equal to 0, we prove that expectation this is equal to expectation of this, which is the true value, okay. Clear? So as a consequence we prove that this expectation equal to this does not depends on the normality assumption. Here we use just one assumption, and that assumption was the expectation of this term is equal to 0, okay. So for the slope we don't need normality in a sense, okay. Now similarly for the variance of the least square estimate, now we are just talking about estimators, okay, keep this in mind, alpha, beta, okay. So similarly if we do the same thing for the variance alpha, we have this form for the for the variance of the predicted value of intercept, and for the variance we have this, and for the sigma from yesterday we remember this is equal to variance of the disturbance term, okay. Now what actually controls our estimator? Is there variability? If the variability has any influence on our estimators or not, okay. So if sigma square increases, if the variability increases, the uncertainty increases in both intercept and slope, okay. So if we have more variability in our data set, the intercepts are more uncertain, okay. And the second thing, the variability of the estimator depends on the spread of the regressor, okay. How much the values is far away or closer to the fitted line, okay. As in here this term appears in the denominator, okay. So if you have more variability here, you have less variance, okay. Now to prove this, that the variance of the estimator beta is equal to this term, we use the same notation as before, beta hat is equal to beta plus this term, okay. Now this is the property of variance, okay. Adding a constant term to a variance does not change the variance, okay. The variance is the same, but if you add a constant, it's just shifted by that constant value, okay. So we have this term. Now to take the variance, okay, take this to the other side, variance of beta hat minus beta, okay, which is equal to the variance of this term now, okay. and by the property it does not change if we multiply it with a constant. Okay, and also now we know from yesterday that the covariance between two disturbance term is 0. There is no correlation between them. Okay, so it turns out that since the covariance is 0, the variance is then what? The sum. If the variance of the sum is equal to the sum of the variances, okay, if there is no correlation, then we hold this property. Okay, and by scaling property of variance, one can say that the variance, if you multiply it with a constant term, the result is the constant term becomes a square, and it's a constant, we can take it out from the variance and we left with the variance of x. Okay, now apply this to the previous formula. Okay, what we get, if we multiply the variance by a constant term, the constant term gets squared and variance, and then we have variance of the disturbance term, and we know by definition the variance of this term is equal to sigma square. So we have ci square sigma square. Okay, now put everything together. What we said, the variance of beta hat is equal to this term. Okay, and then we said if there is no correlation, the variance of the sum of the variables is equal to the sum of the variance of those. Okay, which is equal to this term. Okay, and then sigma, can take it out because this term is constant. Okay, so sigma, we have this result now. Okay, now the next task is to know what the CI is. Okay, to explore it a bit. So before we assume, we replace this term with CI. Okay, and inside the summation we have CI square. Okay, so we have to take square of this value now. Okay, put this inside, we have square of this. Okay, so square can be now applied to numerator and denominator. So the square and square cancel out, and we have 1 divided by this term now. Okay, yes. What is the meaning of C? We assume that we call this term as CI. Just a constant term, just to make the derivation simpler. Otherwise, we would write each time this term. Where is it? Otherwise, we would write this term each time. Okay? Just to represent it like this. It's clear? Okay. So, we have this now. Now, the formula for variance beta hat is equal to this. Now replace this term here, 1 divided by this. So variance of beta is equal to sigma square. We will use this formula to obtain the variance of the estimated beta hat. Okay. Similarly for alpha, but with alpha we have this term 1 over n, which depends on the number of size of the sample. Okay, so if this term decreases, this means that the sample size is increasing. Okay, and this term reflects how far we are from our mean line. Okay. Now, if we have greater variability in the regressor, in the observed values, the smaller variability we have in the slope. Okay, for the estimation. So we can have a larger dispersion around the horizontal axis. Okay, if we have more dispersion on the x-axis, this means we have more data, we have more information about the slope. Okay, and so the slope then cannot be like a horizontal, a vertical or horizontal. We have more information now. We can cover more data. Okay. here we should not take just the variability as the only thing by which we regard xi as a consequence for our variability. Okay, for example, the reason is if the range of x becomes very large, if we have more horizontal dispersion of our data, we can have some doubts then about the linear relation between x and y for this entire range. So yes, more spread of the data can improve the precision of beta hat, but if we have too much large data and if we have too much dispersion, then it may violate the linear assumptions. Okay, so be careful about that. Now, from the beginning we started with the least square estimations, but there also exist other kind of estimations. The natural way is one can do, let's say, not to do just the sum of the squares of the residuals. One can opt for to go like take the absolute values of these residuals. Okay, but mainly widely in literature and in research, the least square is a preferred way. Why is this? Because by the Gauss theorem statement, Gauss theorem says that the least the least square estimator for alpha and beta are the most efficient estimators in the linear unbiased estimators class. Okay, so it is unbiased, it is linear, and it is efficient. Okay, and the terminology used for this is blue. So B means best linear unbiased estimator. Okay, so we have the smallest variance for the least square case. We assume the linearity must exist in our relations between x and y. The estimators is unbiased. Okay, so the key idea here for the linear least square estimator is that linearity should hold between x and y, and the estimator should be unbiased. Okay, now yes.
Since the variance has to be the minimum, does that mean that is there any chances to have covariance?
In a sense,
Like association
between x and y, yes, there can, but then you should have more variables. Then we go to the multiple regression case, because for now in the simplest case we just have two variables. We have input and output. But yes, yesterday we said there are cases this property cannot hold all the time. As an example, we said yesterday, if you have a turnover and that example. So yes, then there is variability, but also there is some kind of correlation you can find. But those are very rare cases. Okay. Normally for the linear regression, we take into consideration, this is our first premise, that there should be no correlation. Okay, we treat them independent. Just for the example of the 8 supermarket, we say each supermarket is in a different province. Okay, so they are completely independent from each other. Otherwise, one experiment could influence the other one. Yeah. Okay. Why this theorem is powerful? So the Gauss theorem, it guarantees the optimality of the least square estimator. Okay, even though if we don't assume the normality observation, the normality distribution, okay, the normal distribution. Before, when we were deriving this estimator, the least square estimator, we said that the disturbance terms should be normally distributed. But the Gauss theorem said if we don't have the normal distribution, we can still achieve good results. Okay, and the Gauss theorem, instead of normality, it uses these assumptions. Okay, it says the model should be linear, the expectation of this term should be 0, we should have a constant variance, and there should be lack of correlation. Okay? But then the consequence here is this is the key reason why this is widely used in practice. Okay? Now, but in a sense now, these estimators are not, let's say, necessarily efficient in the absolute sense. Why? Because there could be other possible estimators, okay? But they can give you results unbiased, they have a small variance, but they may not be linear, okay? So there could exist other estimators that gives you minimum variance, they are unbiased but they are non-linear, okay? So what we say here, in the case of in the group of linear estimators, the least square estimator is the best possible, okay? And to know the correlation between the two estimators, we can use this relation, okay, to find out the covariance between the intercept and the slope, okay? But generally we say that the covariance is equal to 0 and we consider not to be independent. Okay. Okay. So the estimators, they have some influence on each other, the intercept and the slope, okay? So now why they are independent? We have this equation before, we know for intercept can be found this way. First we find to know the beta, we insert here and we find the value of the intercept, okay? Now this intercept is explicitly depends upon the slope. So if we have slope, then we can find this intercept. So a fluctuation in the slope determines our intercept. Okay, if we have higher slope, intercept could be here. If we have here, the intercept could be here. Okay. Now, additional results. If we assume that normality in the distribution term is normal, okay, and we have, then we can get what? The distributional results for the estimators, okay? And we said before that the estimators alpha and beta are a linear combination of the Gaussian, the distribution term, okay? So once these are the linear combination of these Gaussian components, therefore they themselves are normal, okay? Okay. If we take the normality condition into our assumption, then the estimate of alpha under normality is equal to this term, and for the beta goes this way. And we have derived how to calculate the intercept and the beta before, and these are the variance terms, okay, which we saw before now. Okay, so under normality, this intercept and beta follow these distribution, okay? Now, okay, so we say this, okay, this is the best among all the unbiased estimators, which gives us strong optimality for alpha and beta. But there could be other estimators, but they are non-linear. Okay. Now, in the previous derivations, we saw for the variance of alpha and for the variance of beta, we had this term sigma square. Okay. So, why we need this term now to estimate? To recall our assumptions, the expectation of this term is equal to 0 and the variance is equal to sigma square. So this variance here represents the common variance of our distribution, okay, and it does not take into account the disturbance term, the variance caused by the disturbance variable, okay. So if you want to perform inference, we must estimate this value from the observed quantities, okay, because here what we have, those values which are coming from the unobserved value, we cannot calculate them. So we need a way to somehow estimate those natural disturbance, okay. So to do this, we can take help from our residual terms, okay, and we need to find a way to calculate this unobservable error, okay. So we have two types of error, the true error, which we cannot observe, and then we have the estimated error, which we can observe and which we call the residual, okay. So now the key idea is to do what? Take this residual and we will kind of reconstruct this distribution term, okay. So we will take this error to find this one, okay. Now natural is one can do what? To take the summation of the residuals, square them and divide by the total number and get sigma, the estimate of the variance, okay. But this way, this is biased, okay, it's not unbiased, okay. Why this is unbiased? Because, okay, if we take this expectation for the residual term, when we have intercept and beta, so it now depends on two things. So we have two biases here, okay. So we cannot just take it like square summation and divide it by n, okay. We have to take into consideration the two biases for the slope and for the intercept, okay. So it should take these 2 degrees of freedom, okay. Before we were saying, when we were using just sigma square, we said, okay, this expectation can be equal to n times sigma square, but because of these two, we now have 2 degree of freedom, so it is equal to n minus 2 sigma square, okay. In this way, our estimator now is unbiased, okay. Okay, from where these terms are coming, estimating alpha consumes 1 degree of freedom, beta consumes the other degree of freedom, so leaving behind we have n minus 2 degree of freedom, not n, okay. So to get the real value for the sigma square, we denote it now by s square while taking into consideration the degree of freedom, okay, which is now n minus 2. So the unbiased estimator for sigma square can now be written in this form, okay. Taking the expectation of this is a constant term, get out from here, okay. We have this now, and this expectation we say is equal to n minus 2 sigma square, okay. So these n minus 2 cancel out, so the expectation of this term is equal to sigma square, okay. So here in the numerator we have this term, which is exactly the same term to minimize the residuals, okay. But now what we are doing is to divide it by the degree of freedom, so we can also take into account the real disturbance caused by the unobserved observation, which we cannot calculate directly from our data. Okay? Now, so the problem was, what was the problem? This value was unknown. Okay? So, if this value is unknown, we could not calculate directly this variance. Okay? So, what we did, we replaced this by S square. Okay? Which we saw before. Here. Okay? So, we have changed the definition of sigma square to S square. And now the variance can be written in this form. Okay? Just here replacing sigma square with S square. Okay? And if you want to standardize it, we just take the square root of this value. Okay? So take the square root, we now have SB. Okay? Keep this term in mind. We will use this in the confidence interval, in the hypothesis testing and all those. Okay? So this SB is basically what? The square root of S square, the previous one, which takes into account now the real disturbance, the disturbance caused by the unwanted nature, okay, which we don't want it, which we cannot observe. Clear? Okay. Now, why we take this assumption into consideration, the normality and its consequences? Assume that we have this term and it follows the normal distribution. Okay? And we know that now, since beta is a linear combination of these terms, okay, of the Gaussian errors. So, if this is true, it follows that beta hat itself is normally distributed. So this means if this disturbance term is normally distributed and we are taking this assumption into our model, then beta hat is also normally distributed. Okay? Now we need to standardize it. Why we need to standardize it? Because we need to have a solid foundation. What that means is, if we standardize it, we have a normal distribution. For each standardization, then we have known equations. Okay? Otherwise, if we don't assume the normal distribution, then we don't know the equations each time the distribution is taken. So we kind of bring it back to the normal distribution, and for the normal distribution then we know each parameter. Okay? So to do that, if you remember from the from the normal distribution, if you want to standardize it, it is equal to z x time x minus expectation of x divided by under root of the variance, square root of the variance. Okay? So here, for us, beta minus expectation of beta divided by its under root of the variance. Okay? And we know we derived this value before, so the variance is equal to this term. Okay? So this is the definition for the normal distribution. X minus mu, here x for us is beta hat, minus mu is beta, and sigma square we derive is this value. So this way we standardize our distribution. Okay? Now, similarly, under the assumption of normality, one can say that this distribution with the variance multiplied by n minus 2 degree of freedom divided by sigma square is approximately equal to chi-square distribution. Okay? So S square was this. Okay? We can rewrite it in this form. Okay? But the key point here is the distribution should be normal. Okay, how? If we have in our data set, if each experiment is independently and normally distributed, okay, z1 up to zk, if we take square of each of these terms, add them, this gives us chi-square distribution. Okay, but these terms should be independent, standardized, and normally distributed. Okay, squaring them, adding all of them gives us chi-square distribution, right? And in this case with a 2 degree of freedom. Okay, so similarly here, the problem now is the distribution we found before, the normal distribution ZB. What it has again sigma squared. Okay, and we don't want sigma squared, we want S squared. Okay, yes, so we want it to be unbiased, right? So we replace this sigma square with S square. Okay, and when we replace it with S square, it takes now the distribution of T student. Okay, just by replacing sigma square to S square. Okay, so before we had this, now rearranging and make some derivation, multiplying both sides by this term, we get this. Okay, and when we do the final derivation, this T student now is equal to beta hat minus this. Okay, and in terms can also be equal to the chi-square distribution with n minus 2 degree of freedom. Okay, so now we have for the T distribution, but keep in mind with 2 degree of freedom. Okay, and this 2 degree of freedom comes from alpha and beta. Okay, so the slope takes now this shape, this distribution. Okay, the standardized variance now takes this shape. Similarly, for the intercept, it has a distribution of T student in this form. Okay, and for the variance we have this now. So for alpha and beta we have T student distribution, but for the variance we have chi-square distribution. This is a key distinction. Okay, and each time we replace sigma square with S squared. Now, okay, so all these would, as we said, would help us to build the confidential interval, the confidence interval. Okay, so to compute the confidence interval, we need this normality assumption. Okay, now we know all this distribution. Now the goal here is to use these distribution and build a confidence interval for alpha, beta, and sigma square. Okay, what are our alpha, beta? They are the estimators. Okay, so now we want to build the confidence interval for these estimators. Okay, is clear what we are doing now? Okay. Recall, we have this formula. Okay, so for the first, yes, don't say. Now let's let's derive the confidence interval for beta. Okay, so the starting point is under the assumption of normality. We have this distribution for beta which we saw before. Okay, now if we consider this, which is what the quantile, sometimes denoted by in this way, for the student T distribution with n minus 2 degree of freedom. Okay, you know quantile, we take some part of our distribution. Okay, so we have this for our estimator beta. Okay, now we want to build confidence interval for it, and we take this quantile. Okay, so we have the right tail of our distribution to the right side, and we have a left tail of our distribution. Okay, so we bounded it this way, greater than or equal to this quantile and greater or equal to this quantile, keeping in mind with n minus 2 degree of freedom. Okay. Now, to get rid of this from the denominator, multiply both sides with S beta. Okay, so we have now S beta here and S beta here. Okay. Also, we don't need this value here because this is the estimate which we do before, which we would have calculated before the confidence interval, and we want to make sure if this estimate actually really lies in this confidence interval or not. Okay, so let's take also this out to both hand side. Okay, so the final formula or the final equation to estimate beta in terms of confidence interval, the max value and the minimum value. For the estimator beta, we have this confidence interval. Okay, clear? The value of beta here is fixed but is unknown. We have to calculate this. Okay, these are the two intervals, the two endpoints of our distribution, which we calculated from our data. Okay, but keep in mind this interval, the confidence interval, we cannot build it just by single experiment. We do multiple experiments, and each time we estimate beta, and then we build this confidence interval. Like for the majority of time, our estimate beta lies in this interval. Okay. Again, just to remind why we are using the T distribution here and not the Z distribution. Why? Because sigma square is unknown, and we replace and we replaced sigma with S square. So now we cannot use the Z distribution. Now our distribution become T of the student. Okay, so that's why we're using it. Okay, and if we calculate these values from the data set we had from yesterday, the 8 supermarket, the standard error is 61.09. Okay, just by putting values here in the formula. Okay, here we have it. Yes. No, we are now building the confidence interval. This is just the value of the standard error. Okay, this value is from here. Are you with me? Tell me. So now we are building this confidence interval. For this we need the values, this term, and this term. We are building now. Is it clear? Where is your confusion? Where is your confusion? Where is the missing part? Tell me. We have a formula for this. We derived it before. Sorry?
Slightly? Why not? Yeah, but I don't know what video you have here every time.
You have to.
Yeah, we derive this formula now, but okay. You know, S beta is what? Is the variance, okay? The variance. What we did, we took the square root of that variance. We standardized it. So this is just a standard error. Okay?
Oh,
Okay, we did it before, but this is just standardizing the error.
Formula with standardization.
Yes, the normal variance, but we standardized it. Okay. Now for the confidence interval, if we put the values here in our formula, we get for beta, we have these values. Okay? The two extremes. Which means that if we divided it to a lower units, these all we can do it in MATLAB. Just with one function, you will have all these values. We'll see at the end of the lecture. Okay? So, in a reference to a population, if we increase by 1 cent the price, may correspond to a decrease in sale of 3 units in this case. Okay? And in this case, by 6 units. Okay? So, with 95% of confidence interval, if we consider beta, if we want to be sure 95% that the true value, the estimate value of beta lies 95% in this interval, and we find these values, so it then turns out that for a decrease in 1 cent of price, we decrease sale in these units. Okay, before, if you remember, without these calculations, for 1 cent we had like 4.3 units of decrease. Okay. Now here this interval is relatively large. It's very wide. Why? Because our experiment, we have few number of rows. We have just 8 supermarkets. Okay. If we had more data, we could have. Okay. Now, the same thing is true for the confidence interval for alpha. You have some confusion, you can tell me. Where is the problem?
No,
No, you're laughing, so tell me.
I remember something else.
You're here, be present here, man.
Yeah, okay.
You're distracting me.
So basically, for beta, instead of doing values minus mean divided by sigma, we substitute sigma with s, because sigma is unknown. And
Yes.
So we need s because it is unbiased.
Yes. So we each time for these intervals, and then later for the prediction, we will use, as you were saying.
So the values is beta. The mean is beta hat.
The estimate value is beta hat.
Okay, this yes.
So the estimate is beta hat, and beta is the true value. Okay. So with this estimate, we want to know if really the true value lies between the confidence interval. Okay. Okay, so the same is true for the confidence interval of alpha. Okay. So for alpha, we have the same situation, t distribution. Okay. And it can be written the same derivation as we did before for beta. Okay. But this time we have S alpha, and which is again the standardized with S squared. Okay. And we have now the two tails. Okay. So we upper and lower bounded the alpha. Okay. Yes.
What if not? It's not between the range, is it possible?
Yes, if it's not between these two intervals, this means everything's wrong. Okay? It must be between these two confidence intervals. It could be outside in cases where maybe you add some extra data and then you recalculate the beta. So maybe, okay, all of your data is around the mean, the slope, okay? Now you have extra data. Maybe this time the data is further away from your mean. So with addition of new data, you have to recalculate again the slope. Okay, so this times maybe this confidence interval will not coincide with the previous data. So then you have a change in the confidence interval each time when you do this experiment. Okay? Okay. With 95% of confidence interval for alpha, which is the intercept in the supermarket example, this confidence interval for alpha yields us these limits, okay, these two, okay, and this means that this interval quantify the uncertainty of our intercept, okay, so it can go from here to here, it can take these two values, and again these values, this confidence interval is very further away from each other. We have a big confidence interval because we have less data. Okay.
The more data we have, the smaller it gets.
Yeah, it shrinks.
And this is not related to what you were saying before about when it's too much variability. This is something else.
Each one has some effect on the confidence interval. So yes, of course, because okay, if you see,
Because you were
we have,
previously saying that it's good to have variability, so it the
but not too much. But
So
not too much.
When is it too much?
Okay.
Because now it's too little, but when is it too
Yes.
much?
Then we have to assess. We need to find a critical value, a kind of threshold, and that threshold we know by the value of p. We then find the p. We calculate the p value, and that determine us. Okay, you have this threshold. Beyond this, you cannot go. If you go beyond this, that is not a good case. We will go to this. Okay. Now the confidence interval for sigma square. Okay, we said we can find this by the chi-square distribution. Okay, similarly to alpha and beta, we take this quantile, okay, with n-2 degree of freedom, and we construct the confidence interval from here, okay, which takes this shape. Okay, so this is the chi-square distribution, which is greater than or equal to this term, okay, to the left hand and to the right hand. To both we have a chi-square distribution, okay. So half here, half here. If we have 5%, if we have 95% of confidence interval, this means that 1 minus gamma, so 1 minus 95 is 5%. Then we divide the 5 by 2, so gamma by 2 in the other cases. So we have half here and half here of that 5% towards both tails.
So we have 2.5% of error on the left
And 2 on the right. Okay, so they are kind of symmetric. Okay. So we have tracked the chi-square distribution between these two extremes.
Are these also like in the normal distribution 1.96, the quantile 1.96 minus?
Which one you are referring to?
No, the current slide we were, no.
Okay. Here?
In the slide we were last line we
Here.
yeah.
Okay.
Are the values of key try to
0.025.
equal to minus 1?
Yeah, the same, but just a kind of interpretation. So, in the one sense, you say, okay, if you add these two terms, 0.975 plus 0.025 equal to 1. Just a kind of, you could say here minus 0.025 also to the other side. Make sense?
No, I mean, are the values of try to equal to the normal distribution 0.5 minus 1.96 and 1.96, the symmetrical 1 time?
Yeah, they are symmetric in both cases, yes. That's why our beginning point was the normal distribution. So we begin from the symmetry and we end with the symmetry. Okay, so just make some rearrangements here. Okay, we have this. Okay, now what we do, we invert the terms to change the sign of inequality, and now to get rid of this term, we multiply here and we multiply here. So we have a confidence interval then for sigma square. Okay, clear? The same way we did for alpha, we built confidence interval for alpha, we built confidence interval for beta. Now we are building confidence interval for sigma square. Okay? And if we do the calculations, we have these values. And in MATLAB for this we use the function key to E and V. Okay? Key to E and V and the function now. Keep in mind we had n minus 2 degree of freedom. In the example of the supermarket we have 8, n equal to 8. So 8 minus 2 equal to 6. Okay? If you put in this function 6, you will get these values for the confidence interval for sigma square. Okay, are we good now? And if you remember, yesterday we did this for SSE, SSR and those terms, we had this value. Okay, now if we take 95% confidence interval of sigma and we compute then the lower end point, the extreme lower end point and the upper end point, we get these values which we can find taking this value dividing by this value of the quantile. Okay, similarly for the upper limit, taking this value divided by the lower limit. Okay, so we get the lower limit here. Okay, and once again the same case here, because we have few numbers of rows, so we have large intervals. Okay. Often now what we don't want in many cases sigma square, but we want the standardized version of it. Okay, we want sigma just. So to get that for the confidence interval, what we do is just to take the square root of those confidence interval. Okay, and then we have the standardized values for the sigma square. Okay, which is now sigma. Okay, so sigma is what? Sigma square is the variance and sigma is the standard deviation. Just to summarize, for the confidence interval of beta, we use t distribution. For the confidence interval of alpha, we use t distribution. For sigma square, chi-square distribution. Okay, and for sigma then we do this square root kind of transformation. Clear? Okay. Now, moving to hypothesis tests. Okay. And why we are doing hypothesis testing is the problem to assess the significance of our regression parameters. Okay. How much significant our estimated parameters are. Okay. So hypothesis test here, basically we want to assess the model performance in terms of the parameters. Okay. We want to check whether a parameter beta or alpha, the value we estimated is the real value or not, or it is different from the one we estimated. Okay. We know now from the hypothesis testing we have two tests. Okay. The first one is the null hypothesis, the second one is alternative hypothesis. So in the null hypothesis, what we do, we assign a value to our parameter. In this case, for example, for beta, we say beta is equal to beta naught. Okay. So in the null hypothesis, we a priori define a value. Okay. And then we do our tests. If our test says the results of our test are equal to the value we fixed a priori, we accept the null hypothesis. We said, okay, yes, this is true. If the tests we perform and the value is different from the null hypothesis, then we say no. We reject the null hypothesis and we accept the alternative hypothesis, okay, which has two-sided of the distribution. Okay. So in case of the confidence interval, for example, if the confidence interval for beta does not contain the value we fixed a priori, beta naught, then we reject null hypothesis. If the case is opposite, we don't reject the null hypothesis. Okay? Is it clear? Okay. Yes.
Just in case we reach zero, the null hypothesis is wrong, what should we do again?
Then we opt for the alternative hypothesis.
Okay, which is H1.
For example, like you fixed a value for the beta. We say beta, the slope is equal to 0. Okay, and you do your tests. You do the t-test, you do the p-value, and then we have other parameters we need to test. And those results are not in favor of beta equal to 0. Okay, if they are against this, then we reject this hypothesis null and we go for the alternative. We say no, this is wrong, the rest is true. Okay, is it clear? Okay. Now I want to make sure if I understood your point. Okay, so for example, in that case, if beta is 0, okay, so the null hypothesis we say is equal to 0. In the alternative case, we say it is not 0, it is different from 0. Okay, so now we have to test this. To test this from the t-distribution, we know that beta hat minus beta naught, this is our a priori value divided by the standardization. Okay, if beta is equal to 0, this term is equal to 0, so we have beta divided by this. Okay, and this term we have defined before, which is the standard error for beta hat. Okay, and under the assumption we said that this is t-distribution which has n minus 2 degree of freedom because we have alpha and beta in our model. Now the rules for rejection and the rules for acceptance here in this case are: if we reject hypothesis null, which means that beta is equal to 0 in favor of what? We say the alternative is true. If you want to reject hypothesis null, okay, and we want to say the alternative is true at a significance level gamma, okay. So what would be that condition? That condition would be the absolute value of the t-test is greater than this quantile, this value, okay. If this is true, then we reject hypothesis null and we accept the alternative, okay. Where this is because of the t distribution, okay. So if this value is bigger than this, we reject null hypothesis, we accept the other one, okay. Okay, so this t student distribution is symmetric around 0, so we have the left and the right tail, okay. And we said this before, we divide this by 2, so we have half and half to both sides of the distribution. Okay, now in case we do not want to reject hypothesis null, okay, if we say okay, we don't want to reject hypothesis null, then we conclude that the slope coefficient is not significantly different from 0, because if in our equation yi equal to alpha plus beta xi, if beta is equal to 0, we have no slope. If we have no slope, this means there is no relation between our data, okay. This is the consequences if beta is equal to 0, okay.
And that's why we said 0.
We set 0 to test it if it's true or not.
Yeah, but that's the reason that we choose 0.
Yes, to find out if there is a relation or not. If there is a relation, then our model makes sense. If there is no relation, then the model we build doesn't make any sense. Alright? Okay. So yes, we said this. Normally in any software packages, whether it's MATLAB or R, this ratio is usually called T ratio or T statistics, okay. Now, what does mean statistically significant, okay? If the null hypothesis, if we reject the null hypothesis, one can say that the coefficient is statistically significant, okay. If we reject the null hypothesis and we come to the conclusion that beta is not equal to 0, this means our test has some statistical significance, okay, and that significance is we have a slope and there is a relation, okay. Now, in the case of the same data set for the supermarket, if we calculate this value, which is minus 6.917, okay, here, this value, okay, and which is this way, okay, which is this, clear? Now we fix what? A significant level at gamma equal to 5%, which is 0.05 to test it. If TB is greater than that quantile, so that value is 5%, okay. And we have n minus 2 degree of n minus 2 degree of freedom, we have 6, okay. If we do this, we have this value, okay, at a 5% of at gamma equal to 5, okay, which we call critical value. And we do it for both sides of the tails. So for example, for one side of the tail with n minus 2 equal to 6, we have this value, Okay, so now we calculated these two values. Okay, TB, which is minus 6.917, and at 5%, at gamma equal to 5, the quantile value is this, the critical value is this. Okay, so this means that this value we have calculated sorry, this value we have calculated is greater than the critical value. Okay, so TB, this value is greater than this. Okay, so what does this mean now? We said if this value is greater than this, we reject the null hypothesis. Okay, so this means that beta is not equal to 0. Okay, and it makes sense for our data. Okay, because we had a relation. Now, why everything here is dependent on gamma, the critical value I'm talking about? Okay, it also depends on other things, but the main contribution is from gamma. Okay, so generally if the value of gamma decreases, we had 5%, if it decreases, it turns out that this gives us bigger value. Okay, if gamma decreases, the output of this value increases. Okay, what does this mean is a smaller gamma, if we have much lower gamma, the rejection region becomes much larger, much more extreme, and it's then very difficult to reject the null hypothesis. Yes, but you have to lose so much, and it's more extreme. Like you're looking for, I don't know, 100% of precision. So in that case, for example, if before we had gamma 5%, let's take a much lesser value, gamma equal to 0.01%, which is this value. And if we calculate its value, it is 9.02. Okay, it's much greater than now. Before,
it's easier to reject the null hypothesis.
in this case, yes. In this case, yes, because now we see at 0.01% we have this value. Okay, which is extreme value. Okay, it's clear. Now, the other thing here is, what is this threshold? So, for example, or before that, the natural question which you were asking before is, what is the threshold, this threshold and its significance beyond which one would lead to accept the null hypothesis? So, what is that value? Where shall we stop? Okay, so for this reason we have to stop, and we have to put everything, we have to calculate the p-value. Okay, like for example, choosing gamma 5%, as you were saying, 0.01%, where we should do it. So if we calculate the p-value, which is easy, just one line in MATLAB and you have the p-value, which is this. Okay, this means that if the null hypothesis is equal to 0, if beta is equal to 0 were true, meaning if beta is equal to, if this statement was true, then we would observe this value 6.9 with probability of 0.04%, which is very less probability. Okay, if this probability was high, if this p-value was high, okay, then the consequences would be to accept the null hypothesis. but the percentage that this value to be more extreme is 0.045%. Okay, so which is a very low percent.
So even when the null hypothesis proven to be true, and if we have like probability very low, we reject the input.
Yes. So you mean if the null hypothesis is true, and the p-value is very low, yes, then we say, okay, the null hypothesis, we accept the null hypothesis in that case.
But the probability is very low.
Okay, this is another case here. We
So
say,
do we
if,
reject it, or
let me try to re-explain it.
okay.
If we say the null hypothesis beta is equal to 0, if let's say this is true, then to obtain this value, its percentage, its probability is 0.045%. If this was true, you're getting my point.
Okay.
Where you're confused now.
No.
Okay, restate it what I said.
Huh?
Restate it what I said.
Okay, so you said when the hypothesis is proven to be true.
The null hypothesis.
The null hypothesis.
In case it is true.
In case it is true. And when we calculate the TI on that one, I think.
Yeah.
Yeah. And we end up with 0.6.
So it's very low, right?
No, it's
very
very low. This is why I'm telling you, should we accept it or go to the other hypothesis?
Yes, we go to the other
And
hypothesis.
this is my point.
Okay. We're good now. Okay. So we have a very low probability here. Okay? And that's why then we go for the other alternative. We say that one is not correct, and we go for H1, which is alternative hypothesis, right? Okay. Now, so the conclusion here is we have p-value and we have critical regions. So from a critical standpoint, we should look to this condition. Okay, this value should be greater than this, okay, to reject null hypothesis, and the p-value should be less than the value of gamma. Okay, then we reject the null hypothesis. So in our case, the gamma was what? 5%. P-value was 0.04%, right?
Gamma is arbitrary.
Yes, it depends, but typically you choose it 5% or 1% in this range. Otherwise, if you choose big value, this means you are coming inside the bulk of your data. Okay,
So,
and yes,
what will be the p-value accepted one? 3%, 10%, 20%?
this is this condition. If you want to reject the null hypothesis, this p-value should be less than the value of gamma.
Oh.
And the same is true for now for the alpha. Okay, we do the same procedure for T alpha. We get this value, and at gamma equal to 5, 95% of confidence interval, we have this value. Okay, and the p-value is this. So again, this value is bigger than this, and this value is pretty much smaller than the gamma. Okay, so we reject the null hypothesis, and we can do all this inside MATLAB with this function. What we do here is put our x value, y value, inferential, and the value of the confidence interval, which is 95%, we say 0.95. Okay. Now, so what we did, kind of summary of everything is available for you. Now the next thing is to test our whole model, our whole regression model. Okay. And to see, so before we were doing what? To see each parameter of our model, alpha, beta, sigma. Now we want to know the overall regression model. Okay, is it significant? Is it not significant? Okay. To do that, we fall back into the usual things we had before, SSR and SSE. Okay, and this will give us a new distribution, and based on that new distribution we would know the significance of the whole model, and which is called the Fisher distribution. Okay, which is basically signal to noise ratio. Okay, and the same holds here. SSR, which has 1 degree of freedom, because SSR just depends on beta. Okay, and SSE is sum of squares of errors, which depends on both. Okay, alpha and beta, so we have n-2 degree of freedom. SSR, sum of the squares of regression, depends just on beta, and the other one depends on alpha and beta, so we have n-2. So to find out the value of Fisher, SSR divided by SSE, but now we have to take into consideration the degree of freedom. For this case we have 1, for this we have n-2. And what this means, this is the variance explained per degree freedom. Okay, so variance explained per degree of freedom, and this is the residual variance per n-2 degree of freedom. This is the Fisher. Okay, and if you want to do the hypothesis testing with the Fisher, again the same. We choose null hypothesis. For the null hypothesis, beta equal to 0. If beta is equal to 0, in this case the Fisher distribution has now this distribution. Okay, so it depends on 1 degree of freedom and -2 degree of freedom. Okay, so if we calculate this value and this is greater than this, okay, this means that our model has a high significance. Okay, again the same, we do it in MATLAB with these functions. Okay, which is similar to this one. We use this function where we put these degrees of freedom 1 and 6. Okay, and for the 5% of confidence, for the gamma equal to 5, 95% confidence interval, this Fisher value is 5.98. Okay, and we know how to calculate these terms by now. So let's put everything here. We get F value equal to 47.846. Okay, so what we said, if this value of the Fisher value is greater than this, okay, the condition was this, if you remember, this condition. So this is the Fisher value, and here we put our critical value, gamma equal to 5%. If this is greater than this, and which is true, okay, so we reject the null hypothesis and we conclude that our model has validity, there is relation, and we have described everything. Clear? The Fisher value can also be found in this way, which is equal to the square of the t statistics. Okay, So just square that value. That value was 6.91 this, which is approximately, if you square it, approximately equal to 47 point. Okay, and if you find the p-value for this one, we get again 0.045, which is much bigger than this value. Okay, so we reject the null hypothesis. Okay, so the decision here is, since the probability is very close to 0.045, we reject the null hypothesis and we vote for the alternative hypothesis. And okay, functions in MATLAB. Okay, you can do it in two different ways to calculate Fisher or whatever you want to calculate. To do it manually. Okay, first calculate SSR, then do SSE, divide both of them, do it manually. The fast and quick way is to use the function fit_lm. And when you use this function, put the degree of freedom, the values, the other arguments, you will have everything in one go. Okay. Now let's move to prediction now. Okay, and here, okay, these are the results when you put everything in MATLAB. Okay, it gives you everything. Okay, if you use the function fit_lm, the outputs are the estimates. These value we have seen. Okay, the t statistics value, the p value, it gives you everything. Okay, so we had the number of observation 8. We have to put these as arguments in the fit_lm function. Degree of freedom should be 6 because we have n-2. And for the root mean square error, if you want to calculate root mean square error, we have the same SSE divided by n-2, but just take the square root. Before it was what? S squared. Remember, we replaced S squared in place of sigma squared. Okay, now we have S squared. So just take the square root of both hand side, you have root mean square error. Okay, and similarly the fit_lm function also gives you all these rest of the values. Now okay, you can find all those in MATLAB. Okay, similarly, to build the confidence interval, you have this command. Okay, coefficient confidence interval, and then this, you will get a matrix like this, where you have for each of them, for alpha the lower bound, the upper bound, for beta the lower bound, the upper bound. Okay, so just with one line you have both the confidence interval. Okay, in which are like this. And the command ANOVA gives you these results. Okay, the Fisher value, the p value, the mean square, and everything. Okay, now what time it is? Okay, we need to go to the last thing, prediction. Okay,
Here is the matrix.
yes,
In here is the matrix.
yes, you have to define before. Now prediction. The main objective of this linear regression was to predict. Okay. So we need to make prediction, and those predictions should be reliable and reasonably precise. Okay. So let's start from the beginning. So we summarize everything of both lectures and we touch the final prediction. Suppose that we have a sample of observation, we fit our linear line, we fit our linear model, and now our target is what? That we have a new entry, we have a new variable, we have a new observation, and what we want to predict this new observation. New observation is x0, and its prediction, its output is y0. Okay? This is our data. So as an example, for example, our x value is the price of gasoline, which is in euro, and we want to predict its consumption in liters. Okay, but at some point we want for a new value which is not present in our data set, and we want its prediction. For example, to predict if the price is changed by 5 euro, what's the estimate of the consumption then? Okay, so we have two possibilities for this. Value of x naught, the new value, it can lie inside within the range of our data which we have collected before, or it could be outside of the range. Okay, in both cases we should be very careful about this new value, so it should respect all the assumptions and everything we stated before for our data. So it should not be a value, I don't know, very far from the point cloud we have. Okay, alternative way could be to make new observation. Don't predict, but insert a new value into the existing data and rerun your regression line, and you get the price for that. Okay, so similarly, just for the estimation case, we had a point estimation and confidence interval. Similarly, in the prediction case, we have point prediction and we have interval prediction. Okay, to predict some kind of interval in the future, or to predict a specific point in the future. Now, why point prediction alone is not enough? A point estimate usually is limited to the use of any indication of precision. So you have a point and that's it. Okay, and it is essential for any kind of prediction that one should say, okay, this is my prediction, but this is the prediction error. So you should have a range, and that range should define how much you are deviating from the predicted value. Okay, if you remember, we calculated r square for this to know the reliability of our fitted value, but it is necessary but not sufficient. Okay, now to predict with the new value, which is x naught, so x naught be as a specified value of our regressor. Our regressor are the observed value, and which should give us y naught as a predicted value, as an output value for this new value x naught. Okay, what we do for this is to build our linear regression model, and in place of this x now we put the new value, which is x naught. Okay, we know alpha and beta are the unknown parameters, so what we did, we have to calculate alpha, beta, and then we have the random component which is unpredictable. We don't know nothing about this error. Okay, so there are now two sources of error which comes to our model. Okay, we know that alpha and beta are unknown, we can estimate them. Okay, we now have all the tools to estimate them. So estimating these two values of alpha and beta are the first source of error. We cannot estimate them precisely 100%. There must be some error. Okay, so this is the first source of error. The second source of error is the random disturbance, which is coming from outside. So we have two sources of errors here. Okay, and the disturbance term, which is coming from outside, which is a random variable. Okay, so strictly speaking, if the value y naught is not unique, it can take any value. Okay, because x naught, the new value, is a random variable to our model, is a random value to our model. Okay, but okay, these are just kind of notation. Okay, So these things are clear, we formulate it, okay? With this, we introduce new variables, x naught, y naught is the target, x naught is the observed value. We then say what we want to do. Are we trying to do interpolation or extrapolation? Is the new point is inside the data or is it outside of the data? Okay. We then distinguish between the point prediction and the interval prediction. Then we identify both sources of error. Estimate the first error is because of alpha and beta. The second error is which we cannot reduce. Okay. And then we wrote our model like this. Okay, so for predicting the new value, the first thing is to calculate the residuals. Okay, we do calculate the residuals this way. Okay, and if we expand this is this. The residuals is defined by this, but our linear equation is this. Okay, and the predictor is this if we ignore the disturbance term. Okay, let's put these all together here. We have this, do some simplification, and we obtain this. So for the residuals can be obtained this way. Okay, so which is the difference between the predicted intercept minus the actual, predicted minus actual, multiply by the new value now. So now we have a new value and we would have a new residual. If you remember, for each observation we have a residual. We have 1 point here, 1 point here. Here we have a regression line. So for this point we have a different residual. For this point we have a different residual. Now we have a new point here. Maybe the new point is here. So first we want to calculate the residual. And we know that the expectation of the residual is equal to 0. That's why it's unbiased. Okay, and this variance can be written in this form. Okay, we will see how and why this is written. Okay, and this is what the variance of the prediction error. Okay, let's say we predicted, but now we want to know how much it varies, how much its deviation is from the true value. So the variance of the residual can be found by this formula. How is it? We have this. Okay, alpha, beta are constant. Okay, let's remove them. We have this now. And now we know from a random variable, if we have a variance of A plus B plus C, we can write it, it's like this. Variance of A, variance of B, variance of C, 2 times covariance of AB plus 2 times covariance of BA plus 2 times covariance of CA. Okay, for us A is minus alpha. Okay, beta is this term and C is this term. Let's replace everything now in this 26. Okay, so we get that formula. If we replace everything here, it turns out to be this. Okay, so this gives us the variance. Okay, and we know that the covariance between the estimator and the error term is always 0, whether it's alpha or beta. So the error term or the estimator has no effect on the random error, on the random and the disturbance term coming naturally has no effect on the intercept and has no correlation. Has no correlation. Okay. The disturbance term coming from outside has no correlation with the intercept and the slope. Okay. We recall these formulas. The variance for alpha is this, variance for beta is this, the covariance is this, variance is this. Okay, we know these, right? We derive them. Now insert these values back into this formula. Okay, Okay, we put it here. Okay, the variance of alpha, we know, variance of beta, we know. We put all of these. Okay, then we do some simplification, take sigma square out from each term, then we left in the numerator these terms. Okay, so note that this term, the numerator here, it is what? A square plus b square minus 2ab. So it can be written as a minus b whole square. Okay, if we simplify everything, what we have, the variance of the residual, the error, is equal to 1 plus this term. Okay, clear? Okay, so this means that the variance is minimized when x naught is equal to x bar. If the new value is near to the mean, we have less variance. Okay, and it increases non-linearly if this value is further away from the mean. Okay, so if the new value is very close to our mean line, we have minimum variance. If the new value is further away from the mean line, we have much more variance. Okay, and then it's very difficult if this point is very far from the bulk of your data to predict it. Okay, it's easy if this point is near to the mean line, very easy, good precision, we are good, and our uncertainty is less. Okay, now as before, if you remember, we replaced sigma square by s square and we estimated the variance. Okay, but now for the predicting error, we replace it by here. Okay, the same thing, we will use s square. And the purpose here is to make it unbiased. Okay, so for the prediction interval, we have these observations. Okay, now we can build it the same way. Remember what we had here, s beta and s alpha. Okay, the standardized error. But now our error is what here? Under root of the variance of this error. Okay, the standardized one. Okay, so the same thing here, but here we should have y naught minus y hat. We bring y hat here to know this interval. Okay, so this is for what? For prediction interval, the same way we did for alpha, beta, sigma square. Now if this is used just for point prediction, and if we want to build the interval prediction, then we go to those interval to this case. Okay, as previously he was mentioning this, the width of the prediction is symmetrical. Okay, again the same thing, if x moves away from the mean, so you have much more variability, much more variance, because it's directly related to the variance. It's in the numerator, not in the denominator. Okay, we said this. So now we say the sample size also affect, because it's in the denominator. If it is very large, you have large variability. Okay, and these are the three terms of the prediction variance. Okay, we know by this now. Now the goal is, if we have 2 points, new points, okay, to the same data set of the supermarket, we have 1.52 and 1.80. We want to, with 95% of confidence interval of probability, we want to know the interval at these observations. Okay, so the goal here is to construct a 95% prediction interval for these 2 new observations. Okay, in MATLAB, what we do, we follow these steps. We fit our data. The new values are these. okay, and we want to predict this, and we want to know what the confidence interval, okay. So the prediction is what? This, the new values, okay, and what we want, the next arguments are predictions and observations, okay. This is these two arguments are required to compute the intervals, okay. It's specifically required for the new observations, okay, and in output you will get this, okay. So the first row is the confidence interval for this value. The second row is the prediction interval for this new value 1.80, okay. So by default this function consider the variance of this equal to 0, okay. But if you want to include and if you want also to take that error into consideration, that's why it's necessary to put these two arguments, okay, the prediction and observation. And the error plot, the error bands, if you want to plot them, you take the price, the sale and the fill, and then you do this, the error bars for what? For the observed value, for the independent variable, for the dependent variable, take the confidence level, and then vertical you would see the errors, okay. So the prediction interval, we know we are good. Let me try if to see it in action. Do you have any question? No? Okay, so this was our data set. You can access this via GitHub. Okay. Meanwhile, let me try to run. Okay, you take your data, the first column, the second column, okay. So first you just make a scatter plot of this, okay, and then this, okay, to know with 95% of confidence interval between this, you just need this function, okay, and you will get the output. Then we saw MDL, which is what fit the line, and we put our data. We display it for confidence interval. We use the same data. Okay. Now, yes.
Does the fact to the trend?
Yes, in a sense, yes, you can say. Not in strictly speaking like machine learning, but you can say. Can you? I can't hear you. Okay, let's do it after the lecture. Okay. And just to show you, because we have 5 minutes. try to run it. You will get all those plots, okay, and the results. Okay, this is what our confidence interval. Okay, so we had those two new values, and they lies here. And for the rest, okay. So manually, if you want to do it, you have the values of x, you have values of y, you do calculate all those things, SSE, SSM, SSR, okay? So it shows you also all the manual steps, okay? We have the R square, which we said was 0.88, okay? And this, okay. And here, if you can see on this one, okay, here, if you see these are our new points, okay? 1.52 and 1.82, okay? So the point lies here, okay, and it has an error interval from here to here, from here to here. Okay, good. We stop here and see you tomorrow in the lab.